Welcome to all in the lecture series of functional analysis. Now in this lecture we see the example of a Banach space, that is the LP space is a Banach space. The statement is the linear space LP is a Banach space with the norm of x equals to summation I is from 1 to infinity mod of xi I to the power p whole to the power 1 by p, where x equals to the sequence xi I is from 1 to infinity with the element of LP. Here we have to show that the linear space LP is a Banach space with the norm defined like this. Now in solution, let p greater than or equals to 1 be a fixed real number. The LP space, it is called as a sequence space because in this space every element is a sequence of either real or complex. That is, LP space equals to the set of all x such that x is a sequence, its ith element is xi I, that is an infinite sequence of real numbers, that is xi I belongs to R or C, such that mod of xi1 to the power p plus mod of xi2 to the power p up to so n, it is lesser than infinity. This is the definition of the LP space. That means every element in this space is an infinite sequence of either real numbers or complex number satisfying the condition that mod of xi1 to the power p plus mod of xi2 to the power p up to so n, it is lesser than infinity. That is, we can write it as, that is summation I is from 1 to infinity mod of xi I to the power p, it is lesser than infinity. This sum is lesser than infinity, that means this sum must be finite. That means this sum is converges. This is the definition of the LP space. It is called as a sequence space. Now here we have to show that the LP space is a Banach space. In last period we see that Banach space is nothing but a complete norm linear space. That means we have to show that LP space is a complete norm linear space. To prove that it is complete norm linear space, firstly we will show that LP space is a norm linear space. To prove that it is norm linear space, we have to show that it satisfies the norm defined like this on LP, satisfy all the properties of a norm. So the first property of the norm is norm of x, it is greater than or equals to 0. So we start with norm of x. By definition here, norm of x equals to summation I is from 1 to infinity mod of xi I to the power p whole to the power 1 by p. As here x is the element of LP, x is the element of LP, therefore x equals to the sequence xi I is from 1 to infinity. Here each xi I is either real or complex, and therefore the absolute value of this xi I, it is always greater than or equals to 0, and this is true for all I. Now mod of xi I, it is greater than or equals to 0, therefore its pth power, that is mod of xi I to the power p, it is also greater than or equals to 0 for all I. As mod of xi I to the power p, it is greater than or equals to 0 for each I. So the sum of all these mod of xi I to the power p, that is summation I is from 1 to infinity mod of xi I to the power p. It is also the sum of non-negative terms and hence it is also greater than or equals to 0. Now this sum is greater than or equals to 0, therefore its pth root, that is whole to the power 1 by p, it is also greater than or equals to 0, and it is nothing but the norm of x, it is greater than or equals to 0. That means the norm of x equals to norm of x greater than or equals to 0 where x equals to the sequence xi I with any element of LP. Thus the norm defined on LP satisfy the first property of a norm. Now we have to show that it satisfies the second property of a norm, and the second property of a norm is norm of x equals to 0 if and only if x equals to 0. So we start with norm of x equals to 0. Now norm of x equals to 0 implies that apply here the definition of norm of x, that is summation I is from 1 to infinity mod of xi I to the power p whole to the power 1 by p, it is equals to 0. Now the pth root equals to 0, it implies that the term must be equals to 0, and therefore we get summation I is from 1 to infinity mod of xi I to the power p, it is equals to 0. Now the sum equals to 0, but in this sum each term is an absolute value of a real number or complex number. So when that means it is the sum of non-negative terms, and the sum of non-negative terms equals to 0 implies that each term must be equals to 0, and therefore it implies that mod of xi I to the power p, it is equals to 0 for all I. Now the pth power equals to 0 implies that the mod must be equals to 0. It implies that mod of xi I equals to 0 for all I, and the absolute value equals to 0 implies that xi I equals to 0 for all I. And as xi I equals to 0, but xi I, it is nothing but the ith coordinate of the sequence x, and it implies that xi I equals to 0 for all I. That means here xi 1 equals to 0, xi 2 equals to 0, xi 1 equals to 0, xi 2 equals to 0, and all terms are 0, and therefore x, that is equals to the sequence xi 1, xi 2, xi 3, ith term is xi I, and so on. Here all xi i's are 0, that means x equals to 0, 0, 0, 0 and so on, and therefore it is equals to 0. We start with that norm of x equals to 0, and lastly we get that x equals to 0. Now conversely we start with that x equals to 0. X equals to 0, that means all its coordinates are 0. That means all xi i's are 0. It implies that xi I equals to 0 for all I. Xi I equals to 0 implies that its absolute value, it is also equals to 0. That absolute value equals to 0, therefore its pth power, this is also equals to 0. Now it is true for each I, that means for each I mod of xi I to the power p, it is equals to 0. As it is true for each I, therefore their sum, it is also equals to 0, and this sum equals to 0 implies that its pth root, it is 0, and as its pth root equals to 0 implies that norm of x equals to 0. In this way we prove norm of x equals to 0 if and only x equals to 0, and therefore we say that norm defined on LP satisfy the second property, and the second property is that norm of x equals to 0 if and only x is equals to 0. In this way the norms defined on LP satisfy the second property of a norm. We prove the third property of a norm, that is the norm of x plus y is lesser than or equals to norm of x plus norm of y. Here we take x and y. These are any two elements of LP. That means here x equals to the sequence xi I. It is the element of LP, and y equals to the sequence eta I. That is also the element of LP. For these two elements of LP, we have to prove this triangle inequality. Now to prove this triangle inequality, first of all we see the Minkowski's inequality, which we have to use here. And Minkowski's inequality, Minkowski's inequality, that summation I is from 1 to infinity mod of xi I plus eta I to the power p whole to the power 1 by p. It is lesser than or equals to summation I is from 1 to infinity mod of xi I to the power p whole to the power 1 by p plus summation I is from 1 to infinity mod of eta I to the power p whole to the power 1 by p. This is Minkowski's inequality, which we have to use here. Now we start with the norm of x. Norm of x plus y. By definition, it is equals to summation I is from 1 to infinity mod of. Now here the coordinate of x are xi I and the coordinates of y are eta I. Therefore, it is equals to summation mod of xi I plus eta I to the power p whole to the power 1 by p. Here, by using this Minkowski's inequality, it is less than or equals to summation I is from 1 to infinity mod of xi I to the power p whole to the power 1 by p plus summation I is from 1 to infinity mod of eta I to the power p whole to the power 1 by p, by using this Minkowski's inequality. But by definition, it is nothing but the norm of x and it is equals to norm of y. That is norm of x plus y. It is lesser than or equals to norm of x plus norm of y, and it is the triangle inequality. Norm of x plus y lesser than or equals to norm of x plus norm of y. And here the norm defined on LP satisfy the third property, N3 is satisfied, and therefore now we have to prove the last property, that is N4. That is, we have to show that norm of alpha x equals to mod alpha into norm of x, where alpha be any scalar. Norm of alpha x equals to mod alpha into norm of x, where alpha be any scalar and x equals to the sequence xi I with the element of LP. Now we start with norm of alpha x. It is equals to summation I is from 1 to infinity mod of. Now here the coordinates of x are xi I, and therefore the coordinates of alpha x are alpha xi I. So we write here summation mod of alpha xi I to the power p whole to the power 1 by p. It is equals to summation I is from 1 to infinity mod alpha to the power p into mod xi I to the power p whole to the power 1 by p. Now here our alpha is independent of this I, and this summation is taken over I, and therefore as alpha is independent of this I, so we can take it out. We can write down here equals to mod alpha to the power p into summation I is from 1 to infinity mod of xi I to the power p whole to the power 1 by p, and that is equals to mod alpha to the power p whole to the power 1 by p into summation I is from 1 to infinity mod of xi I to the power p whole to the power 1 by p. It is now, it is equals to mod alpha into, now it is nothing but the norm of x. That means norm of alpha x is equals to mod alpha into norm of x, and therefore the fourth property of the norm is satisfied by the norm defined on LP, and hence we say that the norm defined on LP as norm of x equals to summation I from 1 to infinity mod of xi I to the power p whole to the power 1 by p is a norm on LP, and hence LP with this norm is a non-linear space. As it is a non-linear space, but we have to prove that LP is a Banach space. That means we have to prove the completeness of LP. To prove the completeness of LP, we have to show that every Cauchy sequence in LP converges in LP. So we start with the Cauchy sequence. Let sequence xn be a Cauchy sequence. In LP. As it is a Cauchy sequence in LP, that means for each n, xn be the element of LP, and LP is a sequence space. So every element in LP is a sequence. Therefore, for each n, xn is an infinite sequence. Xi1, xi2, ith term is xi I, and so on, where each xi I is either real or complex. Now here, as it is the xn, therefore for this n we write down here the coordinate like this: xi1n, xi2n, xin, and so on, where each xin is either real or complex. Now here we have to show that this Cauchy sequence in LP converges in LP. That means we have to show that xn converges to x is the element of LP as n goes to infinity. So we start with the epsilon. Let epsilon greater than 0 be given. Then it is a Cauchy sequence. Therefore, for this epsilon greater than 0, therefore for a given epsilon greater than 0, there exists a natural number n naught such that for all m comma n greater than or equals to n naught, d of xm comma xn, that is equals to norm of xm minus xn, it is lesser than epsilon. Now we putting the value of norm of xm minus xn as summation I is from 1 to infinity mod of xi im minus xi in to the power p whole power 1 by p. It is lesser than epsilon for all m comma n greater than or equals to n naught. Now here this is the sum of the absolute value. That means this each term in the sum it is non-negative, as well as here epsilon is also non-negative. So we taking the power p on both sides, we get summation I is from 1 to infinity mod of xi im minus xi n to the power p. It is lesser than epsilon for all m comma lesser than epsilon to the power p for all m comma n greater than or equals to n naught. Now here the summation of mod of xi im minus xi n to the power p, it is lesser than epsilon to the power p for all m comma n greater than or equals to n naught. Here in this sum, the each term, that means for each I, mod of xi m minus xi n to the power p, that is the absolute value, it is the non-negative value, and it is always less than or equals to the summation I from 1 to infinity mod of xi m minus xi n to the power p. This each term is always lesser than the sum of all the terms, and this sum is lesser than epsilon to the power p for all m comma n greater than or equals to n naught. And therefore we get that for each I mod of xi m minus xi n to the power p, it is lesser than epsilon to the power p for all m comma n greater than or equals to n naught. This implies that for each fixed I mod of xi m minus xi n to the power p, it is lesser than epsilon to the power p for all m comma n greater than or equals to n naught. Now here again it is the absolute value, therefore it is always non-negative. Epsilon is always non-negative, so we can take the square, we can take the pth root on both sides. We get mod of xi m minus xi n, it is lesser than epsilon for all m comma n greater than or equals to n naught. That means for each fixed I mod of xi m minus xi n, it is lesser than epsilon for all m comma n greater than or equals to n naught. Now we read it like this. For a given epsilon greater than 0, there exists a natural number n naught such that whenever m and n greater than or equals to n naught, mod of xi m minus xi n, that is lesser than epsilon. And it implies that sequence xi m is a Cauchy sequence. It is a Cauchy sequence in as each xi m is either real or complex, therefore it is a Cauchy sequence in R or C. And we know that R and C both are complete, therefore as R and C both are complete, therefore every Cauchy sequence in R or C converges in R or C, and hence the sequence, that is the sequence xi m converges to xi I, where xi I is the element of R or C as m goes to infinity. It is true for each fixed I. That means for each fixed I, xi m converges to xi I, where xi I belongs to R or C as m goes to infinity. That is xi 1 m converges to xi 1, xi 2 m converges to xi 2, up to so on. In general, xi m converges to xi I as m goes to infinity, where xi 1 belongs to R or C, xi 2 belongs to R or C, up to xi I belongs to R or C. Now collecting all these limits, we write down x is equals to xi 1, xi 2, xi I and so on. Now here we have to show that this x is the element of LP. Also we have to show that our Cauchy sequence xm converges to x as m goes to infinity. That is, we have to prove. These two things we have to prove. means we consider norm of xm minus x. That is equals to, as here we know the coordinates of xm are xi I m and the coordinates of x are xi I. Therefore, norm of xm minus x, it is equals to summation I is from 1 to infinity mod of xi I m minus xi I to the power p whole to the power 1 by p. Now here, as we prove, for each fixed I, as m goes to infinity, xi I m goes to xi I for each fixed I, and therefore in this summation mod of xi I m minus xi I, that goes to 0. Xi I m minus xi I, that goes to 0 as m goes to infinity. Using this, that means the summation of this term and this term goes to 0 as m goes to infinity. That means it goes to 0, and therefore this sum also goes to 0 as m goes to infinity. That is, we get that norm of xm minus x converges to 0 as m goes to infinity. It implies that xm converges to x as m goes to infinity. We start with the Cauchy sequence xm. xm is a Cauchy sequence. xm is a Cauchy sequence in LP. And we show that xm converges to x as m goes to infinity. Now the last point, we have to prove that this x is the element of LP. That is, we have to show. Now to show that x belongs to LP, firstly we show that xm minus x that belongs to LP, and by using this we prove that x belongs to LP. As here xm be the sequence xi I m and x be the sequence xi I. Therefore, xm minus x, that is the sequence xi I m minus xi I is from 1 to infinity. Now here we know that xm converges to x, as we prove that xm converges to x as m goes to infinity. We write down this definition in the form of epsilon as, that is, for a given epsilon greater than 0, there exists a natural number n naught such that for all m greater than or equals to n naught, norm of xm minus x, that is lesser than epsilon. Now we put in the value of norm of xm minus x like this. Summation I is from 1 to infinity mod of xi I m minus xi I to the power p whole to the power 1 by p, that is lesser than epsilon whenever m greater than or equals to n naught. Now here this is the sum of the absolute value, that means it is the sum of non-negative terms. Epsilon is also non-negative, so we can, taking the power p on both sides, we get that summation I is from 1 to infinity mod of xi I m minus xi I to the power p, that is lesser than epsilon to the power p for all m greater than or equals to n naught. Now in this sum mod of xi I m minus xi I to the power p, this sum is lesser than epsilon to the power p, and epsilon to the power p, if we write down, it is equals to k, and then this k is lesser than infinity for all m greater than or equals to n naught. That means the sum of this term, it is lesser than infinity. We write down it again, that is summation I from 1 to infinity mod of xi m minus xi I to the power p lesser than infinity. This implies that this series converge. This series converge implies that xm minus x equals to the sequence xi m minus xi I, that is the element of LP. And therefore we get that xm minus x belongs to LP. Now LP is a vector space, and in vector space it is closed with respect to addition and scalar multiplication. Therefore when xm minus x belongs to LP for all m greater than or equals to n naught implies that x minus xm, that is also belongs to LP for all m greater than or equals to n naught, because we know that in a vector space if x belongs to V, that is the vector space, then minus x, that is the minus 1 is a scalar multiplied with a vector x, then it is also the element of vector space. And by using this, here we say that xm minus x belongs to LP implies that x minus xm belongs to LP. Now our x, as we write down x is equals to the sequence xi I, we have to show that it is the element of LP. We write down this x in the form x is equals to x minus xm plus xm, where m is greater than or equals to n naught. Then x is equals to x minus xm plus xm. Now here x minus xm, as here we prove that it is the element of LP. We know that xm, it is also the element of LP. Therefore these are the two vectors of LP, and LP is a vector space and every vector space is closed with respect to addition. Therefore the addition of two vectors of LP, it is again the element of LP, and therefore x minus xm plus xm, that is the element of LP, and it implies that x equals to the sequence xi I, that is the from I is from 1 to infinity, it is the element of LP. Thus we start with the Cauchy sequence xm is a Cauchy sequence in LP, is a Cauchy sequence in LP, and we get xm converge to x is the element of LP as m goes to infinity. This implies that, but here xm, it is a Cauchy sequence which is arbitrary Cauchy sequence in LP, and we get that arbitrary Cauchy sequence in LP converges in LP, and hence LP is a complete metric space. Also we prove that LP is a norm-linear space. Thus combining these two, we get that LP is a complete norm-linear space, and it implies that LP is a Banach space. LP is a Banach space for P greater than or equals to 1. And hence we get the proof that LP is a Banach space.